I'm going to show you how we would use Crunchit in order to do these calculations. So first, let's go to the coffee example. So this was a proportion problem. So we go to statistics, proportion, one sample. Sorry, my mouse is acting funny right now. Now, here we're going to use summarize because we won't have the raw data. And with the coffee example, there were 50 people in the experiment, and we got 36 people to pick the fresh brewed coffee. Now, this time we are going to use this hypothesis test, and you'll put the proportion under the null hypothesis. Now, one thing that is unfortunate about the two examples that I used was that the null proportion was 0.5. It does not have to be 0.5. It can be anything that you want it to be according to the problem. It doesn't have to be 0.5. So here it was, but don't think that it has to be. And then you pick your alternative. So either the not equal to for two-sided, less than, or greater than. Here we thought it was greater than. So we hit calculate, and here's where we see that p-value. And we get a little bit more accurate than we did with the table. We see that it's 0.0009, which rounded to 0.001 that we got in the example. Now for the coin problem, we would go to proportion, one sample. And here he did 4,040 tosses. Oops, that's not what I typed it. And then he had 2,048 heads. And here it was 0.5 again, but remember it can be any value. Read the problem to see what you're testing against. And here we did the two-sided because we didn't know if it was greater than or less than. And here we get a p-value, and we actually got 0.378, so I'm not sure what was going on in the textbook, why it rounded that to 0.37, but maybe there was something that Crunchit does a little bit different. But you'll get the right answer in your homework because the homework is based on the output on Crunchit. We do need to look at one more or a couple more definitions, and it's looking at what's called the significance level. Now, I said that the standard is 0.05, but sometimes that changes based on the context. So you would decide in advance how much evidence that you need to have to go against the null. And we'll talk in chapter 23 how that can be decided. But for right now, we just are going to recognize that there is a significance level. We use that written as alpha. Typically, it's the Greek letter, it's the first letter of the Greek alphabet. And most of the time we choose alpha equals 0.05. What that means is that the likelihood of getting that result is 5% or less if the null is true. Now, sometimes we go a little bit further and we choose an alpha of 0.01. This means we need stronger evidence against the null, where you're getting something that happens only 1% of the time or less. And so that's a stricter requirement. Now, every once in a while, you'll use 0.1, which will be not as strict. You just need it to happen 10% or less. So if you get a p-value that is smaller than that alpha level that you set, either 0.05 or 0.01, then what you would say is that the data are statistically significant at that level alpha. So when you are doing these tests, you need to recognize that significant doesn't necessarily mean important. And that's huge, and that's one of the reasons that p-values are going out of favor, is because people believe that something that shows up statistically significant must mean that it's important. And that's not always the case. Statistical significance only means that it's not likely to happen just by chance. We have that not likely given by a probability, and so a lot of times when you read these in studies, you'll see something like the results were significant, p less than whatever, so that they know what you were comparing that significance level to. And so, like I said, we've chosen 0.05, which is somewhat arbitrary, but it does trace back to Sir Ronald A. Fisher. And he chose that because it was kind of related to that 2 standard deviations from the mean. Now, this p-value does give us a lot of information because it gives us an ability to assess the significance at any level that we choose. And in chapter 23, we'll talk about implications of the different levels that you can choose. Now, one thing to note though is what if you get something that's between 0.01 and 0.05? If you got a p-value of 0.03, then you got something that's less than 0.05, so it would be significant at that level. but it's not less than 0.01, so it would not be significant at that level. So you are looking at small decimals here and making comparisons. But regardless of whether we use 0.05 or 0.01, ultimately, each field has their own widely accepted guidelines for how much evidence is enough. In some fields, p less than 0.1 is plenty. P less than 0.05 is going to be, moderate, and 0.01 would be strong, or the field might specify a required p-value. Now, I've shown you how to use the Crunch It for example 1 and 2, and so I want us to look at the question for the mean. However, I got a little ahead of myself, and we need to talk about the test statistics. So when you do this hypothesis test and you do this in Crunch It, what's happening is, I've lost my place. What's happening is you're calculating the number of standard deviations away from the mean. There we go. So you're getting your standard score. And Crunch It is going to get this to you as an output, but the way it was calculated was by taking the observation, then subtracting the mean, and dividing by the standard deviation. And so that standard score is reported in Crunch It as the test statistic. And there's Crunch It. So the test statistic here is given as the Z statistic. So if the question wants to know the test statistic, you would report it. So here, this means that 0.88 is the number of standard deviations away our observation is. And if we recall from previous sections, this is less than 1 standard deviation away from the mean, so we know that that's not a particularly unlikely thing for us to observe. And so that test statistic is that standard score that's being computed based on the sample data. Now we can talk about the population mean. So whether you are doing a significance test for the mean or the population, or of the proportion, they're both looking at population parameters. You use the same process, the same theory. It's just the sampling distribution will have a different calculation that'll be handled by Crunch It. So what you're doing with these is, since it is looking at the population mean, you're going to calculate the sample mean, and you're going to determine the likelihood of observing that sample mean if your null mean was true. So let's look at the example length of human pregnancies. Now, typically, women are given a delivery date that's calculated 280 days after the onset of their last menstrual period. But only 4% of women actually deliver babies at that 280 days. So, why do we do that? Well, it is a good place for us to start. But what we have found is that a much more likely average might be less than 280 days. So let's see if maybe we should be doing something less than 280 days. So we're going to start with a small sample of 95 women with healthy pregnancies, and we're going to monitor to see how long it takes from ovulation to birth. Now, based on these 95 women, the sample mean is 275 with a standard deviation of 10 days. So the question is that 275 far enough away from 280 for us to think that the mean is something other than 280 days? So we first need to set up our hypotheses. So either the mean is equal to 280, that would be our null hypothesis, or the mean is less than 280, that would be our alternative. And then our sampling distribution that we learned about in chapter 21 tells us that the mean would be 280 with a standard error of that standard deviation divided by the square root of the sample of the sample size, and that gives us 1.03. So we're going to determine our test statistic by seeing how many standard deviations away from the mean that is. So we take the observation, 275, we subtract 280, then divide by 1.03 to see that this is negative 4.85. We are 4.85 standard deviations below the mean, as what we would expect if the average really was 280 days. So that p-value is incredibly small. Look here at our normal curve. A standard score of negative 4.85 is way in the tail with a probability less than 0.0003. So that is definitely evidence against using 280 as the average number of days. Now, I'm not suggesting that we throw out everything that obstetricians use, because this was a small sample of 95, and that 280 might also include some of the other types of births that are going on. So this was just a small textbook example, so don't go throwing out what doctors say. But here we do note that the conclusion is that this p-value is definitely strong evidence that the mean is below that commonly reported length of 280. Now, how would we do the same problem in Crunch It? Well, we would go to statistics, we would go to Z, one sample. We'll do summarized, and we'll use our our sample size of 95 and the sample mean of 275. And then the standard deviation was given as 10. Then we come up with the mean under that null hypothesis. So the claim was that it's 280, and we think it's something less than, so we'll pick our alternative less than. We'll hit calculate, and we'll see that the p-value is incredibly small. It's less than 0.0001. So that is a very small p-value, so we would definitely suggest that it is unlikely that that null of 280 days is appropriate in this example.